So I have 40 minutes, and originally this is a slot for 2 presentations of each 45 minutes. You may have wondered a bit about the title of the slot because there's something like land and soil. Instead, the original titles were land surface processes and physiographic data, which you can see here down on the title slide of that presentation, which is usually presented by Jürgen Helmert et al. You see the name down here. My name instead is Jan-Peter Schulz, and you will see my name a few times here in this presentation to come here and there, because I made several developments in the land surface scheme, which is called Terra. Okay, you will see it soon. And the second presentation originally is about lake processes in the lake model and sea ice, which is coming afterwards. And then this is Dmitry Mironov usually presenting, and he's also the main author of all these models. So I start, so I have to be very fast. This means that I basically, I try to skip basically all the equations, so which you may like for the moment, but you can read them later then in the tutorial or in some other sources or the original articles. So to go, yeah, I don't know, get the main ideas and get the figures, and so I try to convey the main ideas. Okay, so this is the most important document at all. You see here ICOn tutorial by exactly the people you see all the time organizing here, Florian, Daniel, and Günther. So please, this is the main reference. Please look inside this tutorial, and you can find all the information which comes in the presentations you can find there. Basically, Jürgen has particularly also used this part of the slides. Oops. And this, for example, is here one section called Land Soil Model, Land Surface Model Terra. You see here there's obviously organization of the different sections. And okay, it's a bit much text here. Maybe I try to just jump a bit through the main bullets. So the main articles, the main references for the soil, vegetation, atmosphere. Can you see the mouse, in fact? I was wondering if I do this way.
Yes, we can.
Maybe this way is even better. This way, no? No laser pointer?
Yes, looks good.
Okay, perfect. Okay, so you see here the main articles I would like to point, because this you really have to, if you want to work with Terra, with the land surface model of ICOn, and all the, ICOn, global and regional and so forth, no, for weather and for climate. Then the original resources are here, Schrodin and Heise. So Reinhold Schrodin and Erdmann Heise, 2001. This is a Cosmo technical report. So this comes from the Cosmo Consortium, and they have a series of reports, technical reports, and also newsletters. And so this is the original reference. And then here Erdmann Heise and Ali made an update in 2006, and then they both retired. And exactly in 2006. And this was a bit of a problem in DWD because sort of the full knowledge of and experience and the development was retiring the same year. And so we had to recover a bit. Later, then here's an article, Schulz et al. This is me, 2016. You see also the long gap where we had to recover a bit to come back in further development, further maintenance, and so on the model. And this describes parts of the model, basically about the energy cycle and moisture cycle and so forth. So going through this here, okay, this figure shows, you see atmosphere, and then at the bottom here is the land surface and the ocean. So here we focus on the land surface, of course. We see basically the land surface scheme has the task to deal with the energy cycle and the water cycle. Energy cycle you see indicated by these arrows. The shortwave radiation is coming down, partly reflected by clouds and scattered and and so forth. A part of this will reach the surface, will be absorbed, a part of it. That's determined by the albedo. And a bit of the reflected part is then partly reflected, which is determined by the albedo. Okay, so this is the arrow going up again. The surface will be heated at day and cooling at night, emitting long wave radiation upwards. This is the green arrow. And then at the surface, we will have then sensible heat flux and latent heat flux. These are the turbulent heat fluxes, which in the model are dealt by the turbulence and boundary layer schemes, which you will hear later. And this depends very much on the surface temperature. So the key variable now at the interface between the land surface and the atmosphere, or the near surface atmosphere, is the temperature, the surface temperature. There are different ways to specify or to define these. Some people call it skin temperature, some people call it LST, which is a satellite remote sensed value than land surface temperature, or other concepts. So is a lower boundary condition for that flux, and based on the surface temperature, usually one uses the Magnus formula or something similar to compute the saturation specific humidity, meaning the moisture which is available then, and this computes then the moisture flux and then also the latent heat flux, which is the latent heat transported by the moisture flux. And this is then a potential rate, and you will see later some stress factors which in fact will reduce the potential rate to the actual rate. So you see several things. So radiation, exactly as I said, biophysical control. This means that in fact we have here at the land surface, we have vegetation and non-vegetation, and maybe also mountains and glaciers and rocks and so forth and lakes. But particularly the vegetation is an issue on its own because they can transpire, so they actively participate in the surface moisture cycle. And they have a stomatal control. Stomatal control meaning if the soil gets too dry, if the plants, trees particularly, they don't have water available enough anymore for transpiring, they close the stomata, the so-called stomata. These are small pores on the leaves. This can be opened or closed actively. And this concept we have in the model. And exactly, in the ground we have several layers. Maybe I will then jump directly to the slide. Oops. Okay, exactly. Showing the layers that will show soon. Then now snow. There's a one-layer snow model. This is the operational one. There's work going on a multi-layer snow model, which is still under development, but is very much proceeded now. And so in next years, the same training here, then at some point that will become the multi-layer snow model. Exactly. And it needs physiographic data or external parameters, as we call them. You see this word XPAR here. This is the external parameter, soft. Again, taken from the tutorial here, you see there are different raw data sets, like for orography, aerosols, NDVI, which describes the vegetation, the season cycle, soil data, so soil type or soil texture is called. The lake distribution, the lake depth, surface albedo comes from MODIS, and different land use data sets optional. Land uses or land cover describes, you can see the map, the distribution of vegetation on the land surface and other land use classes, and we have several raw data sets available. At the moment, this globe cover is the operational one. Here would be a map of this, and here you can read the sources. And again, Smeartech published two articles describing this more. Originally, it comes from Arsensio Mesmer here. Okay, topography. Okay, this is H-surf is the height of the surface. Okay, tile approach. This is a very interesting feature. If people who remember or heard about the Cosmo model, in the Cosmo model there was not a tile approach, meaning every grid element had exactly equations on the scale, meaning there were no subscale information within one grid element where you could compute, for example, subgrid scale fluxes. Instead, in ICOn, you see the figure here on the left side. This upper panel should show the realistic landscape, as you saw on the raw data set before. There's the land cover data set would indicate that there's some agriculture, there's some forest, there's some lake, there's some grass and so forth. And when you scale it down to the model grid, now this would be indicated here by the square. This would be one grid element, which is now representing this piece of surface. Then all these land use classes are sort of counted by their fractions as much as they cover. Does Terra include any carbon-related process? No, does not. The reason, because Terra is already developed for NWP, for numerical weather prediction, and there we make short-range forecasts up to 2 days or maximum 7 days, and we assume that in this 7 days, the carbon-related processes do not play a role. Instead, climate exactly there plays a role. This would be a different land surface scheme. Okay, here now the tile approach, go on. Then you compute the fractions of, you're welcome. I see here the chat popping up, that's why, sorry, if I'm a bit interactive here. You see now, for example, the yellow one here is down the yellow and so forth. Looks like a cake, no? Or a round cheese, and you cut this one in these sectors. And now the sectors, then you can see here, for example, that grid element. The outer ring now would represent a triangle, which would be the ICOn original grid. And this is close to Falkenberg, in Falkenberg, which is an observatory of DWD, a bit east of Berlin, which is a very good place because there's many measurements available. So the outer ring indicates then the sort of the realistic fractions of the land use inside this triangle. Now, in ICOn, you can specify the number of tiles you want to use. Our default value, the usual one which we use in the operational, and usually also the test cases and everything, is 3. That's why now we take the dominant 3 classes, which is here this green, this yellow, and this brown, and produce the 3 tiles, which are here now inside. The rest is thrown away, so it's discarded. So this is not considered. Meaning now that it's a rescaling, and now you see that this green, which is before maybe, I don't know, 1/3 or something, and so forth, and now scales up to a bit more than 50%, and the yellow and the green similar, I don't know, about 1/4 or something, and the rest is gone. You can also select more tiles, then you would also capture the next one, here the rosa, then the green, and so forth. But it turned out that the verification also results show usually that 3 tiles are a good number to make the model perform well. Okay, this is tile approach, very important because very grid element now in the land surface has 3 tiles usually in the operational and with 3 different land use classes. The interesting part is now the 3 different land use classes, they compute their own surface temperatures and also their own turbulent heat fluxes. So now we have 3 subgrid scale heat fluxes, for example, sensible or latent heat fluxes, which are representing then the 3 different columns, and these also go into the ground. The columns go down through all the layers in the ground to the bottom, and meaning they have different temperature profiles and water profiles in the ground and the vertical, depending on the land use class, which is on top. And then to the atmosphere, there's only one value. In the atmosphere, we have only one column standing sort of on top of these 3 tiles, subgrid scale. And meaning we have 3 different land surface temperatures, and over them above of them, we have only one atmosphere temperature. Meaning the fluxes are computed using the same atmospheric temperature, and then afterwards the subgrid fluxes are aggregated, so to produce the grid scale flux, which is then seen by the atmosphere. Okay, later here we'll see also the advantages of this approach. Here a different example. This is here Northern Africa. This is the Egypt, the Nile Delta, and then you and Claudia Becker, in fact, here. So the names on here from Lindenberg, Falkenberg. So they made this work, and meaning here in this yellowish or I don't know skin color. Then you see the tile approach, which will be produced from this. Instead, the desert here, the gray or bare areas, as you can see, here's the legend for the different colors. So this gray would be bare areas, so Sahara, I mean desert. In the end, the full grid element will only be bare area, Sahara. So the model now sees only Sahara. In theory, there was, or in practice, there was a little bit of yellowish, which is rain-fed upland, likely, but this is discarded. Okay. Summary XPAR, you can read or better you read later in the tutorial. Okay, I go on. So now Terra, land surface model. You see here a bit the time-stepping scheme of the ICOn model. So you see a big part dynamics. This was, you heard already, so this was content of other presentations. Then fast physics. We have 1, 2, 3, 4, 5 light blue boxes in the fast physics. This means that they computed every time step every D time step. One of them is land lake sea ice. We are here now in land lake sea ice. You see other slow physics, you see all these other ones. They have different time steps which can be selected. Now we jump here in the land lake sea ice. These are the 3 tiles. So the left 3 columns here would be the tile 1, 2, 3. So which is needle forest, for example. Some other more vegetation and some grassland. And you see also the layers in the ground. You see the numbers. Here the numbers are in yes, meter. So this is the top layer is 1 centimeter deep, and the next one is 2 and 6 and so forth and so forth. And you see the roots, the root depth here of the different vegetation. So the tree have deeper roots and the grass has less deep roots. The other 3 tiles are potential snow tiles. So when there's snow, then you see this rosa colors, boxes. This would be that there are some dynamic snow tiles. So a snow cover can be there or not. So this here is the famous land surface name list. So land, LND, name list, NML. So these are several switches you can select. Looks a bit much in one go, but of course after a while one gets used to this and the meaning of the things. Exactly, some examples will come now. So now it looks a bit full here. Terra energy budgets. So we have the land surface. Now we take again the first layer here. Here's the second layer. This is 1 centimeter deep. So we have a temperature which is here in the middle. So each layer has a temperature in the middle and the water content and the frozen soil water content here and so forth down to 7 layers usually. There may be a snow layer, a single layer snow on the top. This at the moment we don't consider. So we have the sensible heat fluxes here, solar radiation, sensible and latent heat fluxes. In the old times, just to give an example now, the surface temperature, which is seen from the atmosphere from above, was the temperature of the first soil layer, meaning the one in the middle, meaning the one in ½ centimeter depth. So the 1 centimeter here, so in the middle was ½ centimeter deep, meaning the long wave outgoing radiation here and also the latent and the sensible heat flux, particularly sensible use the temperature, was using the temperature which was in ½ centimeter depth. This has a problem. That's because there's a thermal inertia. The real diurnal amplitude of the surface temperature cannot be resolved, meaning the amplitude, the diurnal amplitude, which I try to indicate here a bit with the mouse, was too low and a bit delayed in phase. Because the real surface temperature is sort of up here at the surface somewhere, or at the surface of the snow, or in case of vegetation, then on top of the vegetation, or somewhere in the upper part of the vegetation. And there can be a high diurnal cycle of the surface temperature, which then is in our case called skin temperature, and which I will present here in the next slides. So this here is now the heat conduction equation in the ground, meaning from this temperature to the temperature of the next layer, there's heat conduction going on. This is driven by this equation, this heat conduction equation. So TSO, sea soil, the difference or the variation in time is determined by this equation. This is the heat flux going from one layer to the next. This is the gradient, so exactly the vertical gradient of the surface temperature. This is the heat conductivity, lambda, very important parameter, and this is then the divergence of the flux. And this together gives the continuity equation or heat conduction equation. Discretized looks this way. So this is then T soil of layer 2 minus T soil of layer 1 is divided by the difference in depth here, gives the gradient times the heat conduction. This is the ground heat flux from the surface. And this gives then the ground heat flux given here. So the upper boundary condition here for the first level, and this is then the change of surface temperature. Okay, we have a name switch which is called I-type heat cont. You can see the default value is 3 exactly. And this means the 2 meant that the lambda here is not constant. 1 means lambda is constant. It's just depending on the soil type. Soil type may be sand or loam or clay. And there was a lookup table in the model which tells for each soil texture, there's a particular value for lambda. Equal to 2 means that this conductivity depends on the soil water content. the wet soil has a very high conductivity for temperature and also for soil water, by the way, and the dry soil has a very low. And this is treated if you choose here the number 2. Number 3 instead is described here a bit. Here's a piece of the source code of Terra, which explains also the 3. You see here type of soil thermal conductivity. You see my name here. So this is this article I mentioned before. You can read something in that article. And you see here also the number 2, the number 1, the number 2, and here's the number 3. And this is the PhD thesis of Johansen from 1975, which is nowadays state of the art still now of exactly all the models, basically worldwide NLP models and climate models. You use this in the ground. Another example for naming switch is this I-type canopy. This also I introduced. Before equal to 1 means that the soil surface temperature is used, as I said before, the temperature value in the top soil layer in the middle, which has the deficiencies of not resolving the dynamic cycle correctly, which was always visible in the verification of our models over all the years. I don't know, I was always wondering, and then between whatever, 2005, 10, 15, and so forth, that the models have too low diurnal cycle, and also compared to the ESMDF model, this was always visible when comparing the old global model, GME against IFS, there was always visible that we underestimate the diurnal cycle in the amplitude, which was always strange. And what to do against this one? In fact, then originally I made a PhD in land surface modeling, so at the Max Planck Institute in Hamburg for meteorology, and there was already an article around at that time for Viterbo and Bayes, 1995, Journal of Climate, which described the new, or at that time new concept of the skin temperature, which they implemented in IFS and made operational, and then they improved the model very much. So I remembered sort of this this concept and published this here in Schulz and Vogel. Vogel is my colleague from Lindenberg-Falkenberg, and we could use the data. So in 2020 we published this. And also made it operational. The main equation is this one. You see here the upper boundary condition for the energy fluxes, short-wave radiation, long-wave radiation, latent heat flux, sensible heat flux. And this is here then the temperature in the ground, in the top soil layer, which was before, only this one was there before. And now this concept introduces a new temperature, skin temperature, T skin. And these two temperatures are connected by a parameter, which is called lambda skin, also skin conductivity. And a small value makes a weak coupling. This means that T skin can become very different from the TS, meaning this would be allow a higher diurnal cycle of the surface temperature, and a large value would mean a strong coupling, and then T skin cannot deviate much from the surface temperature. This only allows small diurnal cycle. You see down here, again, taken from the code, I-type canopy, type of polarization with respect to surface energy balance. So the one was the old one. The new one, the number 2, which is still not the default. That's why you really have to set it in this name list switch here. So you have to set the 2, otherwise you run with the 1. Is introduced exactly by, yeah, these authors. I mean, in the end, in Schulz and Vogel, here are the articles. Okay. Snow, there's this single layer snow model. Yeah, okay. Basically, I would like to say here about the albedo. Of course, the albedo for snow is much higher than the vegetation below, so much more radiation is reflected, meaning the temperature can stay cold. Once then the snow is melting, then dark background will come through, or the needle forest, for example, in Scandinavia, where the snow may be on top, will fall down by wind, and then the dark trees come through again, and then they absorb solar radiation and will become warm, and then we get this albedo, snow albedo feedback effect, and the albedo gets darker, absorbs more energy. This increases the snow melt. Increasing snow melt, reducing snow melt again makes more dark surface free, which again reduces the albedo, and so forth and so forth. Okay, and what we have in the model that's interesting is we have aging. We have aging of the albedo. You see that after a while this snow gets more compact, and the albedo gets, the surface gets darker, meaning the albedo gets lower, meaning the snow melt is sort of enhanced. And we also have an aging of the density, meaning the density, so it's, you see that the column is sort of going down, meaning the density inside is going higher, is more dense, and the surface gets darker. And this is together is called snow aging, and the model makes this. So, and this is realistic also. Thermal process for snow. We'll skip, as I promised before. So here's the fraction of snow. You want to know how large is this fraction which is covered by snow. Depending on the saltwater equivalent, SWE is saltwater equivalent. So meaning how much water, if you melt all the snow and how much water is left you have there, this is this one, which is not the same like the height of snow, of course, but less, meaning, and this figure, this curve, you have different functions sort of between these. You see here a paper by Roche et al. 2001 from ETH Zurich that you said, yeah, exactly. So these are measurements, and the model makes one version, which was in the beginning not so this linear simply relation, meaning if the saltwater equivalent is rising to a maximum value, which is here 1.5 centimeter of saltwater equivalent, then the surface cover, here the snow fraction, then rises from 0 to 1 linear. And as you can see here, this may not be so realistic, meaning you want a bit flatter, at least in the upper part. And this is then here provided by this. If you see this, name the switches again, then you can read, and then you find out that it becomes more realistic. And this was introduced here by, or presented by Günther Sengel at ICAROS 2019. Okay, some years. Okay, but please read yourself. Now, water budget of Terra at the surface. So we have all these different water reservoirs. Particularly, we have the layers in the ground, layer 1, layer 2, down to layer 7 in principle. Usually the active layers are 6, depending on name the switch again. Here we have iTab root. This is the root profile. This indicates already that the roots are not the same length, all of them, of one tree. This would be iTab root equal to 1. 1 would mean they are all the same length. They reach all the same layer. This turns out to be not realistic. 2 instead is a so-called exponential profile. This means that the deeper you go, the less roots there are there. So they're not the same length. And this turns out to be more realistic. So this is on. iTab EVSL, this is evaporation from soil. There was formerly, I don't know if this is also coming here, but wrong formulation. So you should for sure use the number 4, which is also still not default, I believe, in the nameless default. So you should, this is a resistance-based formula, which also I introduced together with Gerd, is documented in the same article. This is the transpiration from vegetation. This we had, this is 3. This is the so-called interception reservoir. This is the leaves, they can form a water film on the leaves. And this is called interception reservoir. And the thickness of this is set to this value. Okay, I would say we leave it this way. Hydrological processes, yeah, okay. Again, equations, just make one example. Here is soil water, this WL of level K, so layer K in the ground, is all this budget equation. Here's also soil ice, so the water can also freeze. The snow layer, okay. Maybe it's an example here, this interception reservoir. So we get precipitation falling on the leaves. So it forms a water film. Then it comes also, should be evaporation, or can also be dew. So should be contain both. No? So evaporation would be a source and dew would be a sink. This e-percolation is the water which then falls through. So when too much rain comes down, so it cannot be kept then something falls through. And then will be a source for the upper soil layer. You see the e-perc now is the water, the rain, which is falling through the leaves and reaching the first layer of the ground and can then infiltrate. And this is the water which cannot be kept by it can infiltrate in the ground. No? This one component, in difference from this this is the runoff from the interception store, meaning this is the water which falls down but cannot infiltrate in the ground, instead goes into the runoff. Okay, just to give an idea of the different flux terms here. Water budget goes very similar to the heat conduction equation in the ground. There's also a similar equation, which is called Richards equation, or Darcy equation. In fact, is this inner core. Basically, it's here the same. Look, you see this is the same term, plus this is here, and this is the gravitation. So the gravitation is difference from temperature, which is simply the heat conduction equation, the vertical. The water has an extra force acting up with the gravitation, which is continuously pulling it down. That's why this is extra term here in that equation. The solution, your D and the K have to be parameterized, which is done by this formula. Yeah. Now, one more word to this transpiration from vegetation, which is basically also this flux formulation, this gradient formulation. But there, as said before, there's a stomatal control, meaning this air storm, the stomatal resistance. This is the resistance of the leaf, the little pores, the little holes where the water vapor gets out. If they open this, they do this during the day because they want to make photosynthesis. For this, they open the pores because they want to collect CO2, carbon dioxide. This is very good. So they collect the carbon dioxide, they can make photosynthesis. And the disadvantage is when they open the pores, they lose water vapor, but they need to keep the water, of course. So they have the stomatal control. There are different flux stress terms now, and you can see here different curves. And these are the flux terms. So first of all, it's the radiation. So the sun should at all be shining. And this is this par thing. So it should be the sun shining. Then there's humidity here. This is there's a temperature stress. So there should be around a temperature where it feels. This is the red one here, the T. So in this case, the plant would have a maximum, so a minimum stress sort of. Meaning not stressed, which is here the maximum at 20 degrees Celsius. And if it gets cold to 0, for example, the stress goes down to 0, meaning at 0 degrees, the plant is not able to act anymore. And the same at 40 degrees because too hot. And then we will close the pores, and the resistance here will become big, and then the stomatal resistance will become big. So the resistance becomes big, meaning the flux gets down. Okay, you can read the other flux terms. So in principle, the radiation, the water humidity, the temperature should be in a good range, and there's this the saturation deficit term. This is obviously a bit complicated to understand, so I don't do here. Okay, you get a summary. We had all this question.